Look at the sheer volume of earth exposed in this open-pit mine. To locate microscopic deposits of native gold, operators have to excavate and process hundreds of thousands of tons of raw rock. Pulling the metal from that rock requires a precise, step-by-step chemical extraction method called cyanidation. Done correctly, it isolates the gold to a purity level of 99.999%. In this tutorial, we will map out that entire process. We will cover how to size the ore, master the specialized tank equipment, execute the specific chemical reactions, and implement the strict environmental protocols required at every step. Moving from raw earth to pure bullion is an exact science. Maintaining strict adherence to these operational procedures determines whether a plant runs as a highly lucrative extraction operation or if it suffers a catastrophic ecological failure. Step 1 is mechanical preparation. Operators must heavily crush and grind the raw rock to break it apart and expose the microscopic gold trapped inside. As this scale comparison demonstrates, the ore is mixed with water and ground down into a fine slurry. To expose enough surface area for the chemical extraction, the final rock particles must be smaller than 100 micrometers. At this stage, operators face their first major efficiency hurdle: parasitic minerals. Raw ore often contains high levels of sulfide or carbonaceous materials that will readily consume the leaching solvent before it can ever reach the gold. To prevent that solvent loss, operators run the slurry through a mandatory pretreatment known as the flotation process. This physically separates out the problematic sulfide minerals so they cannot interfere with the next phase. By sizing the ore down to the required micrometer limit and actively filtering out the sulfides, the plant ensures the solvent will target the gold directly. Controlling these physical variables dictates the total financial viability of the chemical leaching phase. Once the slurry is properly prepped, it is pumped into a series of primary leaching tanks. This is where operators introduce cyanide to dissolve the gold, which carries an immediate fatal risk. If cyanide is mixed into a slurry that is too acidic, the reaction instantly produces lethal hydrogen cyanide gas. To eliminate this hazard, operators follow a strict sequence. As this meter shows, lime is added to the slurry first, intentionally raising and locking the pH into a safe alkaline zone between 10 and 11. Only after the pH is locked and confirmed can the solvent be safely introduced. Depending on the ore's specific mineral makeup, the cyanide is added at a highly monitored concentration ranging from 300 to 500 milligrams per liter. The slurry is then continuously agitated using mechanical stirrers or injected air. This physical churning maximizes surface contact between the solvent and the exposed gold. This formula breaks down the exact chemical process taking place in the tank. The combination of solid gold, the cyanide solvent, water, and infused oxygen chemically reacts to strip the metal from the rock, yielding a stable, dissolved gold complex. By aggressively controlling the pH level and maintaining constant agitation, operators safely force the solid gold into a manageable liquid state. Now that the gold is completely dissolved into a liquid complex, the logistics shift. The operators must physically isolate this high-value liquid from the thousands of tons of surrounding waste slurry. Activated carbon acts like a sponge, absorbing dissolved gold over an 8 to 24-hour cycle. Plants use two layouts. Adding carbon directly into active leaching tanks is a carbon and leach, or CIL setup. Isolating stages into separate carbon tanks is a carbon and pulp, or CIP configuration. In both setups, physical dimensions dictate the final extraction. The activated carbon particles are strictly sized to be larger than 500 micrometers. This size discrepancy means operators can run the mixture through mechanical screens. The 100 micrometer waste slurry flows freely through the mesh, while the 500 micrometer gold-laden carbon is caught and collected. Engineering this physical difference makes solid-solid separation economical. Now we have a solid piece of carbon holding highly concentrated liquid gold. The next step is to strip that metal off so the carbon sponge can be returned to the tanks and reused. Operators run an elution process to wash the gold complex off the carbon and then force it back into a solid metal state using a displacement reaction. This is typically achieved through either an electrical current and an electrowinning cell or by mixing in zinc power to trigger cementation. The resulting crude metal is collected and pushed through its final thermal refinement. Through rigorous calcination, smelting, and electrorefining, the impurities are burned away. While the physical gold is secure, the operation is not finished. The extraction process leaves behind thousands of gallons of toxic cyanide wastewater, creating a massive liability that threatens local water sources, wildlife, and surrounding ecosystems. To mitigate this liability, modern facilities are replacing cyanide entirely. This chart illustrates a high-performance alternative called the Jinchan metallic ore dressing agent. As the data shows, it achieves the exact same gold recovery rate of over 97%, but operates with a drastically lower toxicity profile. Because the chemical mechanics are nearly identical, Jinchan acts as a direct drop-in replacement. Operators do not have to replace their existing mechanical stirrs, CIL layouts, or CIP sequential tanks to use it. By transitioning to low-toxicity leaching agents, plant managers protect the ecosystem while maintaining maximum extraction yields, easily meeting strict modern environmental regulations in the process. This is the final result of the extraction and refining sequence, commercial-grade bullion, refined to a highly valuable 99.999% purity. Getting here requires taking thousands of tons of raw earth and applying extreme mechanical pressure and targeted chemistry. The microscopic flecks hidden in the rock are exposed, safely liquefied, captured on carbon, and forged back into solid metal. The foundational chemistry of that extraction has powered the industry for decades, but the methods used to secure the safety of the workers and the surrounding environment are constantly evolving. To learn how you can upgrade your plant's leaching operations with efficient, eco-friendly alternatives, click the link on your screen.